So let us see numerical problem from the section interference. Problem number 15. I will read the problem. A double slit arrangement produces interference fringes for sodium light lambda is equal to 589 nanometer that are 0.20 degree apart. What is the angular separation if the entire arrangement is immersed in water? Refractiveness of water is given 1.33. So actually what happens if the experiment setup is completely immersed in water, then there is a change in wavelength only, and wavelength changes, therefore bandwidth changes. Wavelength decreases, therefore bandwidth decreases, and therefore angular separation will definitely decrease. So answer will be less than that given value. So you can write down the given quantity like this. Angular separation in air is equal to 0.20 degree. Angular separation in water is equal to question mark. Wavelength in air is equal to 589 nanometer. A refractive index, it may be denoted by ANW is equal to 1.33, or you can use it as a 4/3. So actually we know the meaning of bandwidth, fringe width, but here we have to use the term angular bandwidth, angular fringe width. So what is meant by angular fringe width, that now we have to see. So this part is important. Now suppose this is the screen, this is the zeroth broadband, this is the first broadband, zeroth broadband. It is also part of the CBB. So distance between two successive broadband is called as a bandwidth. So beta is a fringe width. Now this is the screen, drop perpendicular. So this is the, say, S1, S2, and this is the, say, point S. So if you turn this line, then this is called as angular separation theta, and this distance is called as the D. So this point is denoted by O, this point is denoted by P, this point is denoted by Q, this is 90 degrees. So in triangle OPQ, angle theta is equal to PQ upon OP. So this is equal to beta upon D, equation 1, where D is equal to distance between screen of observation, where the interference bands are observed, screen of observation, and plane of coherent sources. coherent sources. Beta is equal to lambda capital D upon small d is equal to bandwidth is equal to fringe width. Lambda is equal to wavelength of monochromatic light. D is equal to distance between two coherent sources. This is the question second. Two in one. Therefore, theta is equal to lambda capital D upon small d divided by capital D. So that is equal to lambda upon d. So angular width of fringes theta is equal to lambda upon d. So this formula is required for solving this. So for air, angular width theta A is equal to lambda air upon d. For water, angular width theta W is equal to lambda W upon d. Therefore, so this is equation 3. This is equation 4. So 3 by 4 joules. Angular width in water upon angular width in air is equal to lambda W upon d divided by lambda air upon d. So that is equal to lambda W upon lambda air, that is equal to 1 upon ANW. Therefore, theta W is equal to theta air upon ANW. Therefore, angular width when the experimental setup is completely immersed in water is equal to theta air is equal to 0.20 upon 4 by 3. So 0.20 multiplied by 3 by 4. So that is equal to 0.05 multiplied by 3, and therefore theta W is equal to 0.15 degree is equal to angular width in water. Suffix W is for water. This W for water. So what to find this value? So answer is 0.15 degree. So why I have made star? Because this equation, angular width of the fringes theta is equal to lambda upon d. This d is the separation between the two coherent sources. It in diffraction phenomena it is also called as a slit width. So I will add this distance as a d. D is the distance between the two coherent sources S1 and S2 like this. Next, problem number 16. I will read the problem. In a double slit experiment, the slits are separated by a distance equal to 100 times the wavelength of the light passing through the slits. A. What is the angular separation in radian between the central maxima and the adjacent maxima? B. What is the distance between these maxima on the screen 50 cm from the slits? So, central maxima and next maxima, adjacent maxima. So, we are considering the two successive maxima in bright band like this. So, what is the given quantity? The distance is equal to, distance between the two slits is equal to 100 times lambda. So, small d is equal to 100 times lambda. Then capital D is equal to 50 centimeter. Is equal to 0.5 meter. First part, angular separation or angular width theta is equal to question mark. Second part, the bandwidth beta is equal to question mark. पूरा मागची फिगर आपल्याला करायला. So central maxima first maxima this is O, S1, S2. So this angle is theta, this distance is capital D, this distance is small d, and this distance is beta. Bandwidth. So O, P, Q. In triangle OPQ, theta is equal to PQ upon OP is equal to beta upon D is equal to lambda capital D upon small d upon D, so that is equal to lambda upon beta. So angular separation between central maximum and adjacent maxima is theta is equal to lambda upon d is equal to lambda upon 100 times lambda, so that is equal to 1 upon 100. So theta is equal to 0.01 radian. So this is the answer of the first part. The angular separation in radian is given like this. Now second part, B. Distance between central maxima and adjacent maxima is equal to bandwidth beta is equal to lambda capital D upon small d. But lambda upon small d is equal to theta. Therefore, bandwidth beta is equal to theta into d. So from first part we know that theta is equal to 1 upon 100 or 0.01 radian and d is equal to 0.5 meter. So that is equal to 0.05 meter. So bandwidth is equal to 0.005 meter, or in centimeter it is equal to 0.5 centimeter. So bandwidth is also called as bandwidth. So this is the answer of the second part. Like this. So angular width and bandwidth, the difference between them is this. So in this problem we have calculated both types of bandwidth, angular fringe width and the linear, it is also called as a linear fringe width. Next, question number 18. It is again related with the interference phenomena. In a biprism experiment, the fringes are observed in the focal plane of the eyepiece at a distance 1.2 meter from the slits. The distance between the central bright band and the 20th bright band is 0.4 centimeter. When a convex lens is placed between the biprism and the eyepiece, 90 centimeters from the eyepiece, the distance between the two virtual magnified images is found to be 0.9 centimeter. Determine the wavelength of the light to be used. So we have to determine the wavelength lambda. So in this case, better we will show the given quantity in the figure. So capital D is given 1.2 meter. Y20 is given 0.4 centimeter. So that is equal to 0.4 into 10 into minus 2 meter. V is given 90 centimeter. Is equal to 0.9 meter. Distance between the magnified images is given 0.9 centimeter. Lambda is equal to question mark. So formula is like this. Wavelength lambda is equal to, we know this formula, beta is equal to lambda capital D upon small d. Therefore lambda is equal to beta bandwidth into small d upon capital D, equation E. So D is given directly. Now what is beta? Beta is equal to bandwidth. Therefore Y20 is equal to distance Yn is equal to distance of nth bright band from central bright band, or it is also called as the zero bright band. Therefore Yn is equal to n multiplied by beta. Therefore Y20 is equal to 20 times beta. Therefore beta is equal to Y20 upon 20. So we will keep this value as beta. This is the question. So we know beta. Now D is equal to distance between two slits, that is virtual images. Therefore, the arrangement is like this: S1, S2, the distance is D. Here is a biprism. This is the slit S. This is the lens. And this is the eyepiece. So this distance is capital E. Here inverted magnified images are formed. So S1 has image S1 dash, S2 has image S2 dash, and this distance is the D1. So by this distance is D, because it is the image distance. D distance is U, and D is equal to V plus U. So by linear magnification, D1 upon D is equal to V upon U is equal to V upon D minus U, D minus U, and therefore D upon D1 reciprocal is D minus V upon D is equal to 1.2 meter minus 0.9 meter upon 0.9 meter, so that is equal to 0.3 upon 0.9, that is equal to 1 by 3. Therefore, D is equal to D1 by 3. D1 is given 0.9 upon 3, so that is equal to 0.3 centimeter. So D is equal to 0.3 into 10 to minus 2 meter. This is the equation 6. The D1 is equal to distance between magnified images of the slits S1 and S2. So now putting it, the wavelength lambda is equal to beta is equal to y20 upon 20 into small d upon 70. So lambda is equal to y20 into d upon 20 times d. So y20 distance of the 20 prime point is equal to 0.4 into 10 to minus 2. Small d is equal to 0.3 into 10 to minus 2. D is equal to 1.2 20 multiplied by D is equal to 1.2 meter. So this is equal to 0.4 and 0.6, so this is equal to 0.20, 0.12 into 10 to minus 4 upon 2 into 10 is to 1, 0.12 into 10 is to 1. So this is 1 point. So 0.12, 0.12 will get 10 away. So 10 is to minus 4, 10 is to minus 1, 10 is to minus 1 by 2. So 0.5 into 10 is to minus 6 meter, or 5 into 10 is to minus 7 meter. So 5 into 10 is to minus 7 into 10 is to plus 10 angstrom unit. So that is equal to 5000 angstrom unit. So wavelength of the monochromatic light used is this much. Wavelength lambda is equal to 5000 angstrom. ये एक ही क्वांटिटी आपको डायरेक्ट नहीं ले लेना है. So the theory of linear magnification is required here. So in this figure, S1 and S2 are the two virtual images of the slit formed by the biprism. This is a biprism. So these two virtual images are separated by distance d, and d is not given. We require d in this equation 1, in this equation A. So d is calculated indirectly by using this formula. By linear magnification, size of the image upon size of the object is equal to image distance upon object distance. नेहमीचे सिंबल आपण यूज केलेले आहे. So d1 is given in the problem 0.9 centimeter, like this. V is given, the lens is kept 90 centimeter away from the eyepiece. So V is equal to 90 centimeter. Therefore you have to find U. So D is equal to U plus V. U is the object distance, V is the image distance, D is the U plus V total distance. So this V, distance of the lens from the eyepiece is given 90 centimeter. This it is generated by V. It is the image distance. And therefore we get D. So D1 is the distance between the magnified images. Therefore D must be less than 0.9. So it is only 0.3 centimeter. So now we know D. We know this beta bandwidth. So distance of the nth bright band is given by number of bright band multiplied by bandwidth beta. So we know D, we know beta. Beta is equal to distance of the 20th bright band upon 20. So putting 1 and 2 in equation A, we get this equation. And by substituting, we get the value of the monochromatic light, wavelength of the monochromatic light as 5000 angstrom unit. Next, problem number 20. The intensity of the light coming from one of the slits in Young's experiment is twice the intensity of the light coming from the other slit. What will be the approximate ratio of the intensities of the bright and dark fringes in the resulting interference pattern? So bright band has maximum intensity and dark band has minimum intensity. So we have to find the ratio of I max to I minimum. What is the given quantity? I1 is equal to 2 times I2. I max for bright band, I minimum for dark band. So we have to find this ratio. So we already know the formula for I max and I minimum. Let I1 and A1 be the intensity and amplitude respectively of first light wave. I1 directly proportional to A1 square. I1 is equal to A1 square, therefore A1 is equal to root of I1. This is equal to 1. Let I2 and A2 be the intensity and amplitude respectively of second line. Therefore, I2 is equal to A2 square. Therefore, A2 is equal to root of I2. So, this is equal to second. 1 by 2 views. A1 upon A2 is equal to root I1 upon root I2 is equal to, in a big root I1 upon I2, in a big root I1 is equal to 2 times I2 upon I2. Therefore, this is equal to root 2. Therefore, A1 is equal to root 2 times A2. So, relation between amplitude of the first wave and second wave are like this. Now, for bright band maximum intensity, Imax is equal to A1 plus A2 whole bracket. For dark band minimum intensity distant to interference case I minimum is equal to A1 minus A2 whole bracket square. Therefore, Imax upon I minimum is equal to A1 plus A2 whole bracket square upon A1 minus A2 whole bracket square. Now, using 2 and 3. Using 2 and 3. Imax upon my I minimum is equal to A1 की वैल्यू ही करनी root 2 A2 plus A2 whole bracket square upon root 2 A2 minus A2 whole bracket square. So you can take A2 common. So this is equal to root 2 plus 1 whole bracket square into A2 square. Root 2 minus 1 bracket square A2 square. I2 common bar get the square. So A2 square will get cancelled. So this is equal to root 2 plus 1 whole bracket square. Root 2 minus 1 whole bracket square. The Imax upon I minimum is equal to A plus B plus square root of I plus square root 2 square plus 1 square plus 2 times root 2 multiplied by 1 root 2 bracket So this is equal to 2 plus 1 plus 2 multiplied by 1.414 upon 2 plus 1 minus 2 multiplied by 1.414. So this is equal to 3 plus 2.828. This product is 2.828 and this is 2 plus 1 3 minus 2.828. So this is equal to 5.828 upon this is the 72 1 is so 58.28 upon 0.1.72. So by log, so this is nearly 2. So it will be more than 29. 34 च्या आसपास काही तरी आन्सर येतं ते. By log, this ratio is 33.96 accurate value, and therefore this is approximately equal to 34. So the ratio of intensity of the bright band to the intensity of the dark band is approximately equal to 34. Approximately equal to 34. Like this. So here the relation is given I1 is equal to 2 times I2. So A1 upon A2 is equal to root of I1 upon I2. Amplitude intensity directly proportional to the square of amplitude. This is a common property for all types of waves, longitudinal or transverse, mechanical or non-mechanical. Therefore A1 and A2 they are related like this. So I max upon I minimum is equal to for constructive interference resultant amplitude is maximum A1 plus A2, for destructive interference amplitude is minimum A1 minus A2. So by using this equation 3 we get this simplification. So the ratio of the maximum intensity at the bright band to minimum intensity of the dark band is approximately equal to 34 like this. Next question number 21. You have to make the correction in this problem. A parallel beam of green light of wavelength 546 nanometer passes through a slit of width 0.4 millimeter. The intensity pattern of the transmitted light is seen on the screen, which is 40 centimeter away. What is the distance between the two first order minima? So minimum means dark band and maximum means bright band. So what is the given quantity? Lambda is given 546 nanometer. 546 into 10 raised to minus 9 meter. So then capital D is given 40 centimeter, that is equal to 0.4 meter, and the slit width is given small d is equal to 0.4 mm. 0.4 mm, so that is equal to 0.4 into 10 raised to minus meter. So first we will find the bandwidth beta, and then delta dash is equal to question mark. So we know the formula for bandwidth beta. Bandwidth beta is equal to lambda capital D upon small d. So substitute the value 546 into 10 raised to minus 9 meter. Capital D is equal to 0.4 meter and small d is equal to 0.4 into 10 raised to minus 3. So 0.4 will get cancelled. So this is equal to 546 into 10 raised to minus 9 into 10 raised to plus 3. So 546 into 10 raised to minus 6 meter. 5460 into 10 raised to minus 7 meter. So that is equal to 5460. Okay. Five point 46 into 10 into 10 raised to minus 6 meter. So 5.46 into 10 raised to minus 4 meter. This is the value of beta. Now we have to find the distance between the two first order minima. So the graph is like this. Intensity on y-axis. So this is first minimum. This is first minimum. This is beta. This is beta. This is the width of the central maximum. So beta 0 is equal to 10 meter. So you have to find beta 0. The separation between the two first order minima means we have to find this beta 0. So beta 0 is equal to width of central maximum is equal to distance between two first order minima and the beta 0 is equal to 2 times beta is equal to 2 multiplied by 5.46 into 10 raised to minus 4 meter. So that is equal to 10.92 into 10 raised to minus 4 meter. So that is equal to 1.092 into 10 raised to minus 3 meter. 10 raised to minus 3 that comes answer millimeter 1. So beta 0 is equal to this one. This is approximately equal to 1.1 mm. So this is the answer. So remember this figure 1.1 meter. So I will read the problem. This is the last problem on interference. The distance between the two consecutive bright fringes in the bipedal X1 using the light of wavelength 6000 angstrom is 0.32 millimeter. By how much will the distance change if the light of wavelength 4800 angstrom is used? So two wavelengths are given. Lambda 1 is equal to 6000 angstrom. Corresponding bandwidth beta 1 is equal to 0.32 millimeter. The wavelength decreases to 4800 angstrom. Now we have to find beta 2 new bandwidth. It will be also less than this and then change in the bandwidth delta beta is equal to question mark. So first we have to find beta. So bandwidth beta is equal to lambda capital D upon small d. Therefore beta 2 upon beta 1 is equal to lambda 2 d upon d, lambda 1 d upon d, dd will get cancelled. So this is equal to lambda 2 upon lambda 1, 4800 angstrom upon 6000 angstrom. So that is equal to 4.5. So beta 2 is equal to 4.5 times beta 1. So that is equal to 0.8 multiplied by 0.32 mm, and therefore beta 2 is equal to 2.56 mm. This is the new bandwidth. New bandwidth. This is equation 1. Therefore, change in bandwidth delta beta is equal to higher value beta 1 minus lower value beta 2. So this is equal to this is 0.256. So 0.320 minus 0.256. So that is equal to 0.064 mm. So the bandwidth will change. The bandwidth will decrease by this much value. Bandwidth decreases by delta beta is equal to 0.064 mm. So beta 2 is less, wavelength decreases, therefore bandwidth will also decrease like this. So this is the change in the bandwidth. So here we have completed the problem session for the interference section. Now the last part, theory part, is related with the phenomena of diffraction of light. So next time we will start for diffraction, and then at the end we will see some problem on diffraction like this. Okay, we will stop here.